Everybody, and today we'll do this next topic in this wonderful book, Asimov's New Guide to Science by Isaac Asimov. And we are in the second chapter, Measuring the universe actually. And the subtopic is Measuring a star's brightness. We have already done three topics till now in this chapter. So you can go back to the videos. So let's start measuring a star's brightness. The next major step forward. The next major step forward was the discovery of a new measuring rod. Till now it was parallax and all that, telescope and parallax. The next step, major step forward, was the discovery of a new measuring rod, certain variable stars that fluctuate in brightness. This part of the story began with a fairly bright star called Delta Cephei, Cephei in the constellation Cepheus, Cepheus. Okay. On close study, the star was found, listen to this, to have a cycle of varying brightness. From its dimmest stage, it rather quickly doubled in brightness, then slowly faded to its dim point again. It did this over and over with great regularity. Oh, wonder, no? Astronomers found a number of other stars that varied in the same regular way. And in honor of Delta Cephei, all were named Cepheid variables, Cepheid variables, or simply Cepheids, Cepheids. Not sure of the pronunciation. The Cepheids, the Cephids uh, periods, the time from the dim point to dim point, vary, vary from less than a day to as long as nearly 2 months in a day, dim to dim, some day in a day, and the maximum 2 months. Those nearest our sun seem to have a period in the neighborhood of a week. The period of Delta Cephi itself is 5.3 days, while the nearest Cepheid of all, the pole star no less, has a period of 4 days. The pole star, however, varies only slightly in luminosity, not enough to be noticeable to the unaided eye. The importance of the Cepheids to astronomers involves their brightness, a subject that requires a small digression. So he's digressing a bit. Ever since Hipparchus, the brightness of stars has been measured by the term magnitude according to a system he invented. The brighter the star, the lower the magnitude. Okay. The 12, 20 brightest stars he called first magnitude, somewhat dimmer stars are second magnitude, then third, fourth, and fifth, until the dimmest, those just barely visible, are of the sixth magnitude. Got it? So it's like a lowering. In modern times, 1856 to be exact, Hipparchus' notion was made quantitative by the English astronomer Norman Robert uh, Pogson. He showed that the average first magnitude star was about 100 times brighter than the average sixth magnitude star. 100 times. Allowing the interval of 5 magnitudes to represent a ratio of 100 in brightness, the ratio of 1 magnitude must be 2.512. A star of magnitude 4 is 2.512 times as bright as a star of magnitude 5, and 2.152 into 2.152 or about 6.3 times as bright as a star of magnitude 6. So that's the proportion. Among the stars, 61 Cygni, CYG and I, is a dim star with a magnitude of 5. Modern astronomical methods allow magnitudes to be fixed in the nearest tenth and even to the nearest hundredth in some cases. Sapella or Capella, Capella, is a bright star with a magnitude of zero point 0.9. Alpha Centauri, still brighter with a magnitude of zero point 0.1, and the measure goes on, still greater brightness, which was are designated by magnitude 0 and beyond this by negative numbers. Sirius, the brightest star in the sky, has a magnitude of minus 1.42. The brighter, the lower. Is it clear? The planet Venus attained a magnitude of minus 4.2, the full moon minus 12.7, the sun minus 269. Sorry, 26.9. These are the apparent magnitudes of the stars as we see them, not their absolute luminosities, independent of distance, right? But if we know the distance of a star and its apparent magnitude, we can calculate its actual luminosity. Astronomers base the scale of absolute magnitudes on the brightness of at a standard distance which has been established at 10 parsecs or 32.6 light years. The parsec is the distance at which a star would show a parallax of 1 second of arc. It is equal to a little more than 19 trillion miles or 3.26 light years parsec. Although Sapala looks dimmer than Alpha Centauri and Sirius, actually it is far more powerful emitter of light than either of them. It merely happens to be at a greater distance farther away. If all were at the standard distance, Kapala would be much the brightest of the three. Kapala has an absolute magnitude of minus 0.1, absolute magnitude, actual brightness. Sirius 1.3, Alpha Centauri 4.8. Our own sun is just about as bright as Alpha Centauri with an absolute magnitude of 4.86. It is an ordinary medium sized star. Now, to get back to the Cepheids, in 1912, Henrietta Leavitt, an astronomer at the Harvard Observatory, was studying the uh, smaller of the megalithic clouds, two huge star systems in the southern hemisphere named after Ferdinand Magellan because they were observed during his voyage around the globe. Okay. Among the stars of the small Magellanic cloud, okay, Miss Levitt detected 25 Cepheids. She recorded the period of variation of each, and to her surprise, found the longer the period, the brighter the star. The longer the period, the brighter the star. As this is not true of the Cepheid variables in our own neighborhood, why should it be true of the small Magellanic cloud? In our own neighborhood, we know only the apparent magnitudes of the Cepheids, not knowing the distance or absolute brightness. We have no scale for relating the period of a star to its brightness. But in the small megalithic cloud, all the stars are effectively at about the same distance. Got it? From us, because the cloud itself is so far away. It is as though a man in New York were trying to calculate his distance from each person in Chicago. He would conclude that all the Chicagoans were about equally distant from himself. What is a difference of a few miles in a total distance of 1,000, right? Similarly, a star at the far end of the cloud is not significantly farther away than one at the rear end. Well, the stars in the small megalithic cloud at about the same distance from us, their apparent magnitude could be taken as a measure of their comparative absolute magnitude. So Levitt could consider the relationship she saw a true one. That is, the period of the Cepheid variables increases smoothly with the absolute magnitude. She was thus able to establish a period luminosity curve. Period luminosity curve, a graph that shows what period a Cepheid of any absolute magnitude must have, and conversely, what absolute magnitude of a Cepheid of a given period. A graph that shows what period a Cepheid of any absolute magnitude must have, and conversely, what absolute magnitude a Cepheid of a given period must have. It If Cepheids everywhere in the universe behaved as they did in the small megalithic cloud, a reasonable assumption, then astronomers had a relative scale for measuring distances. This is the detective work. And this was a woman. She did it. She was just a ordinary employee, and her, I think her work was sidelined. She was given credit much later, I think after she died. That was sad part. There are a lot of tragic stories also. Then astronomers had a relative scale for measuring distances as far out as Cepheids could be detected in the best telescopes. If they spotted two Cepheids with equal periods, okay, they could they could assume that both were equal in absolute magnitude. If Cepheid A seemed four times as bright as Cepheid B, Cepheid B must be twice as distant from us. In this way, the relative distances of all the observable Cepheids could be plotted on a scale map. Now, if the actual distance of just one of the Cepheids could be determined, so could the distances of all the rest. Simple. No? Unfortunately, even the nearest Cepheid, the pole star, is hundreds of light years away, much too far to measure its distance by parallax. Astronomers had to use less direct methods. One usable clue was the proper motion on the average. The more distant a star is, the smaller its proper motion. Recall that Bessel decided 61 Cygni was relatively close because it had a large proper motion. A number of devices were used to determine the proper motions of groups of stars, and statistical methods were brought to bear. The procedure was complicated, but the results gave the approximate distances of various groups of stars which contained Cepheids. From the distances and the apparent magnitudes of these Cepheids, their absolute magnitudes could be determined, and these could be compared with the periods. In 1913, the Danish astronomer Ejnar, E-G-N-A-R, okay, Hertzsprung, found that a Cepheid of absolute magnitude minus 2.3 had a period of 6.6 days. From that finding, and using Leavitt's period luminosity curve, he could determine the absolute magnitude of any Cepheid. It turned out, incidentally, that Cepheids generally are large, bright stars, much more luminous than our sun. Their variations in brightness are probably the result of pulsations. The stars seem to expand and contract steadily as though they are ponderously breathing in and out. A few years later, the American astronomer Harlow Shapley repeated the work and decided that a Cepheid of absolute magnitude minus 2.3 had a period of 5.96 days. The agreement was close enough to allow astronomers to go ahead. They had their yardstick. So now they could get at the stars. Beautiful, no? So this is the chapter. So the summary is that how they found out the issues here are the absolute magnitude, the apparent magnitude, the periodicity, the Leavitt curve, right? The point is to open doors like this. I love it. I love Isaac Asimov. He opens a door. You realize, you start getting feelings, you know. I'm now almost feeling like all the stars are in my head. It is really poetic, which is why scientists are so poetic. It's very poetic. Once you feel that, it's a very poetic thing. And it's a power. Knowledge is power, knowledge is poetic. Next chapter is determining the galaxy's size. So man is going ahead, he's going out and not finding the galaxy's size, and then enlarging the universe, then spiral galaxies. These are the subheadings. And then you have the birth of the universe, clusters of galaxies, birth of the universe. So this is how indirectly, with detective work, with observations, with subtle reasoning and comparisons, man's reason finds out, and once he sees it, he feels it. This is the world we live in. Thank you.